Hello guys, welcome back to MJ School of Mining and Geology YouTube channel. In today's session, we're going to be looking exclusively on the geology and the history of the Golden Gate Highlands National Park in South Africa. This is regarded as one of the best geoheritage sites that we ever see in South Africa. All right, it's well exposed in the Upper Karoo rocks, all right, which we call them the Stombek. All right. If you haven't yet visited our video on the detailed explanation of the Karoo supergroup, talking about Karoo sedimentation, how plate tectonics, shaped the Karoo sedimentation, and we've mentioned all the how the Karoo supergroup formed and all the groups ranging from Dwaika, the Eka, you know, the Beaufort, all the way to the Upper Karoo, which is Stombek. And today we are exclusively focusing on the Stombek, which is the upper part of the Karoo supergroup. So please don't forget to like, share, comment, and above all, don't forget to hit the notification button below so that you get notified once we upload new content. Stay tuned. So the Roy Dry, it's one of the geoheritage sites that is preserving the Golden Highlands, all right, park. We are going to be focusing on the geology of this geoheritage site. So if you can check over here, you will see that this is, this is found somewhere closer to, or along the border. Where's my pen? Okay, somewhere here. This is this RD, so it's along the or closer to the border between South Africa and Lesotho. So we are going to be focusing on this area. All right. So please bear with me that this is one of the heritage sites, but we're not gonna be looking at other heritage site. We exclusively gonna be focusing on this Roy Dry. So the geology of the Golden Highlands Park in South Africa is a spectacular this area. It's a spectacular natural archive of Earth history. It records the Earth history. All right, we see the where the dinosaurs such as Massaspondylus were nesting. We get to see how the differences in grain sizes, okay, created, or not only the grain sizes but the differences in hardness created the cliffs that we see in this area, all right, or in this geoheritage site. And then we see the valleys that when the rivers are cutting down. So we are seeing a lot of things which are very interesting to to the students, to the lecturers, to you know, the tourists and many other people. That's why we take the Golden Gate Highlands National Park as the geoheritage site, because it keeps attracting the researchers, the students, lecturers, and many other people. So this it records the early Earth information. So from ancient rivers and swamps to deserts and volcanoes. So you'll agree with me that the Karoo, especially the Stombek, all right, it started with fluvial, into the floodplains, and then we started to have the semi-arid into hyper-aridity. That's what we see in the Clarence, especially upper part, and then now everything was halted, or the sedimentation was halted by um, the the volcanoes. So the rocks here preserve not only dramatic shifts in climates and landscape, but also fossil of plants, insect, and dinosaurs. So this is what we like this area for. It records the evidence of the dinosaurs and the insects and also the plants. So today, weathering and erosion continue to sculpt this ancient story into the golden cliffs and caves for which the park is famous. So the park is famous for the cliff. All right, that's why we say the Clarence Cave. It's everywhere, even in geography, grade 11 or grade 10. I think they're teaching them about these things. The Clarence Cave is one of the famous, geoheritage site we ever gonna have. All right. Yes. And then yeah, and then why the golden? With golden, it's from the fact that towards the when the sun is about to, when it's about to get dark, before that, during sunset, we see the sandstone glowing. So then now into gold, all right, or golden color. Then that's why we say it's a Golden Gate Highlands National Park. So the Golden Gate, it got the name from that. So this is us when we visited this area. So we get to see the caves. All right, we get to see this cave. You see this beautiful cave over here. This and then over here at the top, that's what we call the devil's tooth. So as I've highlighted here, this is the devil's tooth, or what we call the mushroom. It's having the mushroom structure. All right, and then yeah, here over here it's our contact. This is our contact, and it's a confirmable contact. So because here it's a confirmable contact, we see the abrupt change. All right, but in some instances you'll see in a few that will observe the non-conformable conformable formations wherein it will be difficult to identify the contact. But here it's very easy to identify the contact because the rocks are conformable and we see an abrupt change. All right. So here we have got the red mudstones of the Elliott Formation, and then overlain by the sandstones of the you know, of the Clarence. And so this is the basal. All right, this is the basal, and then here at the top is the upper. All right, so the basal is made up of these. We've got these massive sandstones. So we've got these massive sandstones, and these massive sandstones, because they are massive, the massiveness, it could have been because of the bioturbation, and bioturbation would have, destroyed the primary structures. Okay, sometimes in somewhere in these areas we get to see, all of the physical of the primary structures, being destroyed. So this is one thing that we have to take, all right, into consideration. So but now we know that we have the volcanoes that took place in this area. So it could have been that these volcanoes, they baked the upper sandstone at the top, and then changed into a quartzite. And then we know quartzite is resistant. So because it's resistant, now we've got, for the Clarence, we've got two types of grain sizes. We've got the basal, which is soft and easy to be eroded, and we've got the top part of the Clarence, which is resistant. So now it means during weathering, this part sandstone, which is massive, and it's weather just that here it's not clearly visible, but this thing, it weathers into, sorry, I've got a flu, and this thing, it weathers into a blocky structures because of the massiveness. Okay. So the top, this basal part, because it's, soft, it will be easy to be eroded now. But the top part, which is resistant, is coarse grained. This one is fine grained. Okay, so Louis, all right. Okay, this one is coarse grained, then resistant to, weathering. That's why it gives us this cave. So these spectacular sediments, or sedimentation in this area, all right, it's what is good for, giving us these cliffs. All right, but now we also have got these black stains. This is because of the on top of the Clarence, we are having the basalt. We're having the basalts of the Maloti, all right, to Drakensberg, all right, mountains. So we and we know that the basalt is easy to be weathered. All right, there is like intense weathering in the Drakensberg or Maloti Drakensberg Mountain. So that the manganese dioxide from those basalts at the top, it could be the during rainfall, the rain came with those manganese dioxide, leach them, and then get to precipitate them here. That's why it's causing these stains. And these stains of manganese dioxide, they're evident in most of the area in this geoheritage site, right? So let me take my camera back here. Yes, and then this is what you call a cross section of this Golden Gate Highlands National Park. And here you will see that we are having the red mudstones of the Beaufort. All right, the Beaufort is also characterized by the the red mudstones, and then now we having the sandstones, all right, of the Molteno, and then sandstones of the Molteno, and then we start to have the red mudstones of the Elliot. That's what we see there in the picture that I just showed you recently. All right, so we see the red mudstones. All right, and then yeah, and then after that we get to see fine grained sandstone, and then on top we've got the Drakensberg formation. That's where we see the basalts associated with quartzites and sandstones. All right, here the top part. So, but we will be somewhere here. We'll be focusing somewhere here. We'll be focusing somewhere here. All right, will be rising up stratigraphically. All right, but now I just wanted to show you that the Stormberg start from the Stormberg, which is ranging from the Molteno, Elliot, and Clarence. The Stormberg we have having sandstones and mudstones, and then on top we've been red mudstones and sandstones, and we've got fine grained sandstones of the Clarence. Sorry. So the Beaufort and Molteno formations, wherein we're having rivers and floodplains. All right. So the story begins with the rocks of the Beaufort Group. All right. The story begins with the rocks of the Beaufort Group. What do we expect from the Beaufort Group? We expect the red mudstones and sandstones. So these fine to medium grained feldspathic sandstones and mudstones were deposited by high salinity rivers flowing across broad floodplains more than 230 million years ago. So features such as large-scale cross-bedding, clay pellet conglomerates, and fining upward cycles reflect dynamic fluvial systems. So the red coloration, all right, the red coloration we did mention here that we have got red mudstones. So the red coloration of the sediments indicate the arid oxygen-rich conditions. So it means deposition was happening or took place in the arid oxygenated environment. And the abundance of mudstones points to frequent floodplain deposition. That's why we're saying rivers and floodplains. Remember, but I'll show you in a few wherein we're having the river cutting down. It could be meandering or anything, and then you have got the floodplains, and then so it means the ascent were associated with this fluvial, and then sometimes the during flooding, so we expect to see the flooding into floodplains, then depositing these mud particles, and then that's why we are having mudstones in the Elliot, in the Beaufort. Okay. But above this lies the Molteno, well exposed in the eastern and northeastern parts of this park. We see this in the eastern and northeastern parts, right? The Molteno is dominated by coarse feldspathic sandstone laid down by braided river system between 237 and 220 billion years. All right. We are not surprised why we see the braided rivers. So we know if you once watch that video of ours wherein we are defining the paleo environment of the Karoo supergroup, we know during the Beaufort time, during the Beaufort, especially at the towards the end of the Beaufort times. That was when the vegetation that was lost during the Permian mass extinction then was now fully or almost 90% recovered. So now converting whatever the braided rivers into meandering. But now when we enter into the Molteno, that's when we enter into the upper Stombeck. Remember, the Stombeck is characterized by increasing aridity. All right, it's characterized by increasing aridity. So the Molteno, that's why it's still characterized by the rivers and floodplains. And then Elliot, we start to see mostly a little bit of floodplain, but now we are in the semi arid. And now when we are and the environment is still wetter, all right, it's still wetter. That's why now the sediments cannot be, or they are retained on the surface. But once we are in the hyper aridity of the Clarence, that's when the environment was warmer and drier, and now the sediments now were able to be, transported for a longer period of time, all right, or into what you call moving sand dunes. All right, so that's the kind of environment that I want you to picture. All right, so but here we now you see the braided rivers in the Molteno years, because we are still having we are in the arid side. We are in the arid side, meaning we know we've once mentioned the fact that vegetation promote meandering, but erosion promotes braided. All right, but because we are entering into the desert conditions, but now these are not true deserts, still a mini desert. That's why we expected these braided rivers. Its sedimentary structures, such as cross-bedding laminations and occasional pebble layers, record shifting river channels. The Molteno is world, renowned for its fossil record, including the giant fossilized conifers, extinct gingos, the horsetails of ferns, and rich insect assemblages, including the dragonflies with wingspans up to 30 centimeters. So, thick mats of plant debris even formed coal seams, making the Molteno the site of South Africa's earliest fossil fuel discoveries. Okay, so these are some of those things that we've found. This is our Molteno. This is our Molteno formation. We see here we have got these sandstones. We've got these sandstones, right? We've got these sandstones, and yeah, and then also these are the the fossils that we see. So this is the type of an insect, and then we also see these gingos, and we have got these you know the the plant that looks like the cranium, right? Remember, the acrodium was the dominant plant that we get to see when we entered into the Permian, not Permian, but after the Permian mass extinction, when the Closopteris, which formed the vast coal seams in the Eka, then now evolved into, or immediately when it died, it gave rise to this to dicrodium. So it looks like that dicrodium. So the Elliott Formation, here we have in rivers, floodplains, and dinosaurs. So resting above the Molteno is the Elliott, deposited around 200 million years in wetter floodplain, and river environments. So in these floodplains, that's where the dinosaurs, this was the nesting site within the red mudstones. So in pebble to red mudstones and siltstone form steep bended cliffs, while occasional sandstone mark river channels. So these rocks weather into blocky fragments and create the negative weathering slope across the park's hillside, right? The Elliott, right? And then I just wanted to remind people of the, what a floodplain is. So we know the river will keep on cutting downward, will keep on cutting downward, keep on cutting downward, and then these the rivers that we're talking about. But here, that's what we call the floodplains. So these were this is the environment where the dinosaurs were nesting. All right, here the Massaspondylus. So, but when flooding occurs, mud stones or the mud particles could be deposited here. Could be deposited here. That's why the Elliott Formation, we have got these mud stones. All right, we've got these mud stones within the floodplain. The Elliott is one of the richest fossil-bearing units in South Africa, preserving dinosaurs, crocodile-like reptiles, mammal ancestors, and the famous Massospondylus egg nests. The oldest known dinosaurs embryos ever recorded, found in this park. Importantly, this formation records the end-Triassic extinction event when nearly 75% of Earth species vanished during global climate upheaval linked to massive volcanic activities and the breakup of the Pangea. All right. So if you are not familiar with the extinction and life, then 2 days back we have uploaded the video on extinction and life. All right, you'll be able to visualize the extinctions that we get to or the extinctions that we have in geology. At Rodrai, the Elliott Formation is particularly significant. Here, mudstones deposited by meandering streams preserved fossilized dinosaurs' eggs. So these meandering rivers were sometimes flooded. Okay, making it one of the most important paleontological sites in the country. So at Rodrai, the geology beautifully records a transition in environment during the late Triassic to early Jurassic. Right? So different layers of the Stomberg group are exposed here. Why are they exposed? Because they made what you call road cut. They made road cut exposing these rocks in this area. So from the root level up to about 10 meters high, the cliffs are made up of red mudstones of the Elliott Formation. These rocks were deposited by meandering streams that occasionally flooded their banks. Right? So, like I said here, remember, these are the banks. These are the banks. So, occasionally, the flooding was taking place, and then that's where deposition of the mudstone was taking place. Okay, leaving behind fine-grained cells and mud on broad floodplains. So it is within these mudstones that the famous dinosaur egg fossils of Rodrai were discovered, making the site one of the most important fossil localities in South Africa. And in a few, we'll discuss more about these eggs and embryos. Okay. Let me take this one a little bit down. Right. So in this area, that's where they've discovered in this area. That's where they've discovered the X, and then we've got about 7X. We've got about 7X, 1, 2, 3, 4, 5, 6, 7, and then here you see here we see fossils here. We see fossils here. Two of these X showing fossils. All right. We also have got the embryos. We also have got the embryos. All right. So this we just wanted to help you visualize the nesting, all right, in the in the desert, in the floodplains. All right, and then yes, we've got the X. We just wanted to show you so that you are able to visualize. We are having this X, this with the Massospondylus X. So yes, and then they've used what you call CT scan to determine the teeth, to reconstruct the bones, the teeth, and other things. All right, which we will talk about that in a few. So the eggs themselves are small, rounded, and slightly flattened, each only about 6 to 7 centimeter long. These eggs, at large from raw dry, contain at least 7 eggs, two of which preserve embryos. Okay, two of which preserve embryos. Okay, two of which are preserved embryos. In one egg, a nearly complete embryo is curled inside. It's a tiny skull and backbone clearly visible. We clearly see the skull and the backbone. Okay, with arms and legs tucked beneath its body. In another, only the top of the skull is exposed. Only the top part of the skull is exposed. The embryos are extremely delicate. Their skulls measure only about 1 centimeter long, and most individual bones are just a few millimeters thick. Okay, this is what it has been discovered. These 7 eggs were discovered in the red mudstones of the Elliott Formation. Right. So here, what do we see? Um, like I said, we have CT scanning. CT scanning. So synchrotron radiation micro CT scanning. So from this is the equipment having the X-ray source, X-ray beam, and we get the sample here, and then everything is going to be detected by the detector. So studying these embryos required advanced technology. So conventional CT scanning was not powerful enough, or the traditional CT scanning was not powerful enough. So scientists used synchrotron radiation micro CT scanning in France. So this technique allowed each bone to be visualized in 3 dimensions and digitally reconstructed, as I've explained, that they needed to reconstruct these things, showing exactly how far the embryos had developed. So the analysis suggested that the embryos were about 60% developed when the eggs were buried and fossilized. Wow. So they were at least 60% when they were buried and fossilized. All right. Remarkably, even tiny teeth, just 0.5 millimeter long. All right. So you can imagine these like basically beds, they're having these tiny teeth. Okay, could be seen for the first time. So, okay, we are thankful to this synchrotron radiation micro CT scanning. Okay, because these 0.5 millimeter tiny teeth were observed for the very first time. Okay, and of course, even these bones were seen, and so that they were able to reconstruct these bones. The embryonic development of Massospondylus closely resembled that of the modern day reptiles and birds such as crocodiles, chickens, confirming the evolutionary links. So, we've been saying Mesospondylus, but what exactly is this Mesospondylus? Of course, Mesospondylus, you can see this as a long neck. This is a long neck. These long necks, it gives them the advantage. These long necks, it gave them the advantage. How? I mean, think of this. We having, the animals, like, maybe I'm just giving an example, animals with like goats, maybe, or cows, cattle, whatever, you can think of, or maybe rabbits or anything. These things are very small. All right. So if we're having only longer trees, it means those other ones, they were not getting enough food. But the Massospondylus, it was, having or getting sufficient amount of food because of its long necks. It was able to get those plants, or the plants up there. All right. So now making this thing to be rich and strong, so it was strong, and then it was working with the 2 legs, but it can also still work with the 4 legs. So the word Massospondylus come from the longer vertebra, in Greek, and not two, it's usually elongated neck bones. All right, so you see this long neck, and then this early plant eating, it was eating plants. It was eating plants, and it was peaceful. All right, sickle-shaped thumb claws. So it has got this claws. So this claws, the they could be the you know it was it or these cloth were were able to to make the nest, all right, so that it can easily lay the eggs. And then these laws also could have been used for defense, pulling down the branches with what with these laws, and also with the long neck, or even scratching shallow nests in the ground for egg laying. So to create this, to create this, to create this. So to create this, like chickens, chickens, they're making this, yes, something like this. So this way because of the claws. Okay. As a herbivore, or plant eating, Mesospondylus fed on plants. It especially enjoyed ferns, young leaves, and other greenery that thrive in its environment. Its long neck gave it an advantage, allowing it to reach the higher branches and leaves that shorter animals could not, as I've explained. And then most of this of its day was or most of its day was like this spent browsing, nibbling, and munching on vegetation. But as it was doing this, it was cautious to see which other animals can cause harm, okay, to it. Its small, peg-like teeth weren't suitably were not suited for chewing meat. That's why this thing it is plant eater. All right. But exactly like how the normal bats are doing. So this the Master Spondylus, it was swallowing the stones. So those stones, they were helping it to to grind up the food right inside its stomach. So this is the Master Spondylus. So you can see these claws for making the nest, for scratching, okay, and then also it was Master Spondylus. It means it was working with the two. It was working with the two legs, but it can still work with with four, and then long, having this long neck, But you can see, look at, if you were to look closely, you can see that these teeth are exactly like the one of the beds of the bed. All right, so they were not, they were not sharp, as how the animal, not animal blood, but meat eaters would have. Okay, so that's why this thing, it was a plant eater. So adults were, adult measured about 6 meters in length. Wow. So it's about 6 meters. It's about 6 meters, and then a weight around 500 to 600 kilograms. Wow, this was just you know the big animal. And among the most common dinosaurs found in South Africa are rocks of the early Jurassic. That's what we see in the red stones of or the eggs are found in the red stones of the Elliot. Of the Elliot, showing that the during the early Jurassic, that's when we having the dominance of these dinosaurs. All right. So, like I said, also if you haven't yet visited the video on the dinosaurs, in that video of the dinosaurs, that's where we were explaining the extinction as well. We tried to explain and simplify um, the dinosaurs, that why are we having, we started with smaller dinosaurs, and now with time we are having these big or huge dinosaurs. So please go visit that video on MJ School of Mining and Geology so that you get to enjoy these lessons as well. So some of the most remarkable Massaspondilla fossils in the world have been discovered in the Gate Highlands National Park. Now, I'm sure you understand now why this is geo heritage site. Okay, these include the oldest known dinosaurs nests. You saw the nest. You saw the nest here. This one. All right. This one. Okay. Eggs and embryos. See the eggs and embryos. And but now I heard that these eggs are no longer here in South Africa. We are only having replicas. We are only having replicas. So please bring back our eggs, this so that our future children could be able to see these things. I'm not fighting. So I'm kidding. Yes. So we're also having the evidence of these embryos, the eggs, and yes. And the nesting site. All right. If you're to visit the Hodumodumo center, you'll be able to see these things. You'll be able to see these things. So the eggs were laid by Massaspondylus carinatus, a long-necked, small-headed dinosaur that you can see. This head is very small. Small-headed dinosaurs that walked mainly on two legs, but can still walk, okay, at the forelegs. So the geology of the rhodri, above the Elliott mudstones lies a 2 meter thick sandstone, all right, belonging to the Clarence Formation. So these rocks represent a very different environment. By this time, the climate had become warmer and drier, right? And vast amount of fine wind-blown dust called Lewis accumulated across the region. I mean, um, remember, if the environment is wetter, like I said, you are forcing the grain side the scent particles or the grains to be retained on the ground, all right, because the environment is wetter. But immediately when it becomes warmer and drier, now these sediments are no longer retained on the ground. Now they can be wind blown easily. They can be wind blown easily. Then now forming what we call loess. Okay, loess. So these are very fine, a thick deposition of very fine scent particles. Okay, that were deposited over millions and millions of years. So think of these, think of the area, having lot and lot of dust, all right, that will form these very fine this will force these very fine sandstones. So with little water to hold the sediments in place, the dust was worked into into dune fields that spread across southern Africa. So because now we are into the upper, we are into in the Clarence now. So we are having because now the wind can be able to transport these things because they are no longer retained on the ground. So they can be able to be. So we are starting to have what you call the moving sand dunes. We are starting to have what you call the moving sand dunes. All right, but along the margins, that's where we're having the the rivers coming in, all right, the river coming in, giving us the lakes, all right, along the margins, all right. And then here we'll be talking much about, that's where we see, where's my pen, all right, that's where we'll see what you call an egg, all right. In other words, the rocks here record a shift from a flat plains in the Elliott, the flat plains in the Elliott, and rivers, all right, the flat plains and rivers. I got the rivers and flat plains are characteristics of the Elliott, to desert and dunes, the Clarence, because now the environment is drier and warmer, making the sediments to be transported. On either side of the road, right side, you can also see steeply cutting Jurassic dolerite dikes, which intruded about 15 million years later. So, why later? Because according to the principle of stratigraphy, if you haven't yet, if you are new to geology, you don't know the principles of stratigraphy, you can also watch that on our YouTube channel, the principle of stratigraphy. But I always tell people that we bake the cake first and we cut it later on. Okay, so it makes the dolerite to be younger than the intruding rocks. Okay, the rocks are being intruded. So this formed when giant cracks opened in the earth crust, allowing molten magma to rise. So the magma cooled underground into the medium grained dolerite, but its heat baked the surrounding Elliott mudstones and or Clarence stones, altering their texture and texture and color. So these baked zones represent a form of contact metamorphism. Contact metamorphism. We know contact metamorphism is a metamorphism, due to heat. All right. So where existing sedimentary rocks were partially transformed by heat. So this is the road cut which exposed the rocks of the Stormbeck. So if you can check over here, now the contact here is no longer conformable. Sorry. All right. Why are we saying that? We can see now that we don't see abrupt change somewhere. We see gradual changes, and sometimes the sandstone characteristic of or classic or characteristic of the Clarence can still be observed inside the Elliott. So this is our Elliott. This is our Elliott, the red mudstone. These mud particles were deposited in the floodplain. This is the floodplain setting. This is where the Massospondylus eggs were formed, were found. All right, this was the nesting site for the dinosaurs. All right. Then now, on top of that, we're having the massive sandstones, all right, medium to medium grained massive sandstone of the Clarence. This is the Clarence, and here we are having that dolerite dike. So this will be our dolerite, and this will be our dolerite, and then the rocks here are baked. The rock closer to these are baked. So that's where we are having baked rocks. So you can have baked sandstones of the Clarence or baked mudstones of the Elliott. But now the interesting part here is I want you to imagine this. I want you to imagine this. We are having the hot magma which forced its way up. All right. Then as it was going up, it acted like a wedge. So it acted like a wedge. Now, this wedge, it means it was pushing the rocks apart. All right? It was pushing the rocks apart. Which rocks? We talk about Elliott and the Clarence rocks. As this was forcing itself up, it was pushing the rocks apart. So, now, the thinking that I want you to have is if it could be or it could have been that the surrounding rocks were weaker or were already fractured. All right. So the intrusion could make the layers slide a little past each other. What? Along this contact. All right, along this contact. Okay, along this contact with the dike. Now it means it gives us this offset. It gives us this offset. We know normally these things, the layers must be like this, must be horizontal, but now there's offset. Now we see the Elliott a bit up and then the Clarence a bit down. So this is the well-exposed geology of the road drive. All right. So please don't forget about this site. It's very interesting. Like I said, if you have a chance to visit the Golden Gate, please. You are more than welcome. But now you'll be able to see these rocks. I was here. I saw them. I am happy because now I get to see where the most interesting part I don't want to lie. It was the red mudstones where the dinosaurs or the Massaspondylus eggs were found. And not only that, also the myth of the Massaspondylus for Basotho people that it ate, almost all of the village people with the plants and animals. We have a little Senkatana boy who was a hero. Such stories. If you were to visit this geoheritage site, you'll be able to hear them. Please, if you have time, please go visit that. All right. So here I just wanted to show you all of these things. All right. So this is the center. This is the center. This is the Hodumudumo Center. They can take you. They can give you a tour. You will be able to learn a whole lot about this area if you were to visit this place. You will even see the nesting sites or the nest. You'll be able to see these embryos and other things. All right, and the egg replicas. You'll be able to see that. But now here it's well exposed. Here, remember, the contact, we did not have anything that is confirmable. But here, it's confirmable. It's confirmable. Why? Because we've got abrupt change. But here, we did not have that. All right. Look at the color. Look at the colors. Look at the colors. So you can see that these rocks over here are baked. These rocks over here are baked. These rocks over here baked. All right, you can see. And then here we're having red mudstones. So that's where we're having mudstones or siltstones or Louis. That's where we are having not Louis mud, sorry, red mudstones or siltstones. That's where we are having the evidence of the X, all right, of the massive spondylus. And then here we're having the massive sandstone of the Clarence, all right, the massive sandstone of the Clarence, which which are the basal, and because now the environment were drier and warmer, we were able to deposit the very fine materials, and these very fine materials are what gives the cliffs in this area, the cliffs in this area. Why? Because they're soft and they're easy to be eroded, unlike the top part of the Clarence, which is highly resistant, all right, this coarse grained. All right, and then now we are having this a dolerite, which caused this offset. And then here also you can see that this is the Clarence massive stones, and then we've got Elliott Formation red mudstones, and then we've got this dolerite, we've got that dolerite, and then here at the top, that's where you will see the Maloti Drakensberg. Okay, Maloti or Drakensberg basalts. Okay, at the top, which we'll see in a few. And then now this area is somewhere here. This area is somewhere here. It was well exposed by the root cut, and not very far, somewhere here, that's where the center is. Right, and then somewhere here, that's where we see the picture that the first picture that you saw when we first started our lesson. All right, that famous Clarence Cave. It's here, just in front of the center. Yeah, so it's just here. Sorry. So the whole part, this mountain here. So now let's look into those rocks now in greater detail. Now we're having that red mudstones. So I tried to zoom them in so that you'll be able to see them. We have got these red mudstones, all right. And then here we're having the light brown to yellowish brown of the massive Clarence sandstone. I wanted to zoom it in so that you can see it. And then here you are having this brownish with darker grays patches, and lighter yellowish. You have got lighter yellowish in other areas. So this is the dolerite. And then we also have got this baked sandstone. So this we have got these baked sandstones. This correspond to Elliott mudstones, all right, or Clarence sandstone, which were baked by the nearby magma that formed the dolerite dikes. So yes, so these rocks are baked. they have been metamorphosed. So it could be, it could be that we've metamorphosed the mudstone, or we could have metamorphosed the sandstones of the Clarence. Overland the Elliot is the Clarence sandstone deposited between 190 to 185 billion years ago. These rocks mark a dramatic environmental shift as rivers dried up and land transformed into vast deserts. All right, because now the environment became warmer and drier as the Gondwana was drifting towards the north. All right. Towering dunes built from wind-blown sands were compacted into pale yellow sandstones that now form the park's iconic cliffs, such as the Mushroom Rock, also called the Devil's Tooth. Crossbedding within the sandstone captures the movement of ancient dunes, while occasional wetter intervals left thin rivers and lake deposit. I told you that along the margin of that egg, that's where we have got the rivers coming in and giving us the lake deposits. Okay, so the fossil bones are rare here, but dinosaur footprints are common. Footprints are common, recording behaviors like heading and migration. Heading and migration. I mean, you'll agree with me that um, which most of these things, like I said, if you haven't yet visited the video on dinosaurs, you're more than welcome to do that. But in that video, we have explained also the migration part. We have explained the migration part. I mean, think about this. We are in the floodplain. We had food for these dinosaurs, all right, and then in the Elliot, all right, and then they were there enjoying life. But now the environment becomes warmer and drier. It means now the because it's warmer and drier, the wind blown sediments are going to be deposited or covering the vegetation or some of the yes, covering the vegetation. So it means now the food started to become scarce. So if the food becomes scarce, now what will the dinosaurs eat? They would have to migrate somewhere else. All right, that's why we're talking about the heading and migration. So this, like I said, during sunset, we're having this golden or glow golden, or these sandstones which are glowing golden, giving the name Golden Gate. And what did I say about these stains? These are the stains of the manganese dioxide. These are the stains of the manganese dioxide because of the leaching out, all right, leaching out of manganese dioxide from what? From the basalts, from the basalts, from the basalts. All right, we are having that. All right, and then here we are having you can clearly see the Elliot and you can clearly see the Clarence and they are having confirmable contact here. All right, and then this thing they're still cutting down as this river is cutting down, you'll be able to see the rocks of the the Molteno as well. That's why the Molteno in this side it's evident within the rivers. But we also, the Clarence sandstone is weaker than the other rocks, but has been hardened in places by calcification. All right, I will show you in a few. Where calcium carbonate carried by groundwater cemented the grains together. This variation in hardness explains the cliff's dramatic caves, coves, and honeycomb textures as weak zones erode faster than the stronger bends. I've explained this part that the soft, massive sandstone was softer and then it eroded easily, and then unlike the coarse grained resistant rock at the top, okay, or sandstone at the top. So that's why we are having cave because the middle portion keeps on being eroded while the top part keeps on being resistant and that's why it's flat. And then let's talk about the processes which took place in the Clarence. So the cross stratification in ionic system is primarily produced by two mechanisms: grainfall and grain flow. Grainfall occurs when sand grains are transported over the dune crest, being transported here, and settle onto the lee side. They settle here, so it's like this. So they do this, and then they will settle here. They will settle here. then making and settle onto the lee side, forming thin, evenly distributed faucet laminae. Okay, laminae. Sorry about that, laminae. Okay, so grain flow take place when sand builds at the crest. So now the sand builds. Okay, until the lee slope becomes oversteepened beyond the angle of repose. The angle of repose is the angle through which these sand particles or these sediments are no longer stable, and they will what they will do what you call slumping. They will do what you call slumping. Okay, and then that move down slope, that this triggers small scale slumps that move down slope, creating thicker wedge shaped faucet lamina that thins downward. All right, so we're having it's like we're having behaving these we are having this thin, and then we're having something like that, and then all these things they get to forming a wedge kind of vibe. So here I tried to show you that wedging is when you're having something like that. So it's thicker here and then pitching out somewhere. All right. So please note that, and here we having the faucet that were caused by the um during when the the sediments were basically were caused by grain flow, sorry, grain flow and grain fall. But here we are having grain fall because we are having this thin parallel laminate. All right, you can see this thin parallel laminate, and then here this one here, this one is because of second, this whitish material could be that calcification that I talked about. This could it's a secondary. This is secondary. So they came later on to to bind these things, to bind these faucets. All right. So this one is clearly green fall. But now I wanted to show you shouldn't make noise. All right, I wanted to show you these structures clearly, but it was difficult here to observe the wedging. So this was not, the best outcrop to observe the wedging, but at least we're able to see these grain falls forming these thin parallel laminae. Okay, so that's the area. You can be able to determine the paleocurrent here. Can be able to determine the paleocurrent. Okay. So they were clearly visible cross-bedding, but they were not, yeah, basically we saw the cross-bedding in these rocks. All right. So this is what I wanted to show you from the sandstones of the Clarence Formation. All right. Now, around 183 million years ago, immense volcanic eruptions reshaped the region. So sheets of molten lava flowed across the landscape, cooling into dark, durable Drakensberg basalt that caps many cliffs today. At their thickest, these lava flows once built up to 8 meters, 8 kilometers. Was but now forming the backbone of the Maloti Drakensberg mountain. But the heat of the eruptions also cooked the underlying Clarence sandstones, transforming them into quartzite. Quartzite I've already mentioned or described in this part. A tough metamorphic rock in which sand grains fuse together. This hardened layer resists the erosion, reinforcing the cliffs and contributing to the park's rugged scenery. So I've explained this part. I hope you remember. And then now, this is the when we were at the top now. Okay, we're at the top, seeing the the basalt associated with the sandstones, and sometimes we saw the sandstones baked, and it makes sense why they're baked. All right, they're baked. Remember, these sandstones were the sandstones of the Clarence, and then now we are coming in with the lava, now baking those sandstones, Remember, these Drakensberg, these basalts or these lavas were not, it was not once off. No, came and then flow came, flow. That's why um, um, I mean, because people they thought this thing it happened all at once. No, it kept on happening. The This lava kept on extruding, kept on extruding. So that's why we are not surprised when we see the basalts associated with sandstones, but the baking caused the baking caused the the what do you call this, the quartzites. All right. So, but one thing that we also it's of interest here, it's okay. These are the basalts. These, you can see they are dark in color. Okay, because they're mythic. And that's why this area, the people, living around these areas, they can plant, they are having a lot of. So this, sorry, I started from the, okay, from the beginning, but I wanted to show you the sandstones. So I wanted to tell you that the people around these areas, they are having nice crops because of the weathering, the easily weathered basalts, giving the you know the soil the nutrients. So you can see this is the Drakensberg. I just wanted you to visualize it. Okay. So I'm sure you are not surprised why you see the sandstones wrapped by the lava, because that's why we're saying sandstones are associated with these basalts. So you're not surprised. Sorry. Yes. So and then in this one we see the highly weathered, we see the highly weathered basalts. So this is when we were stratigraphically, sorry, up. All right. So we see the highly weathered basalts associated with the sandstones. You will see the sandstones and the quartzite. Or the quartzite were at the bottom. I couldn't take them. All right. So these are easy to be weathered. That's why we see and we see a lot of sand. That's why I'm saying the people who are staying in these areas, their soil are rich, and they can, um have the best crops. So this is the sandstone. This is the sandstone. Okay. Now, can you see that this is resistant to weathering, unlike the basalt? But initially it was almost 8 kilometers thick, but now because of the effect of weathering and erosion, now you know it is reduced in right. The later volcanic activity forced the magma into cracks in the rocks, forming the striking dikes and sills. Dikes cut vertically across the sandstone, while sills intruded horizontally between the bedding planes. At Rodrive, a prominent dike reveals how the surrounding rocks were baked and altered by heat, leaving contact metamorphic zones of hardened, discolored rock. I've showed you that when we were seeing the exposed road cut. And then now, do you see those stains? Do you see those stains? Do you see the blocky weathering? Do you see it? Now the blocky weathering, because of these things are massive, and you see Elliott formation, and you see the cave. We see the cave. Do you see the cave? So yes. So while volcanic and sedimentary process build the rocks, it is erosion that caved the park's present day landscape. Wind, rain, rivers, and streams now away and add softer rocks faster than harder layers, creating overhangs, caves, and sculpted cliffs. River cut deep valleys, exposing the valley, exposing the layers like pages of a geological book. All right, that's what I'm saying. Especially these rivers, because are cutting down, you'll be able to see the volcano within the in the rivers. Black streaks across many cliffs tell a smaller story. These are stains of manganese dioxide leached from basalt above and deposited by groundwater, seeping through the crack, the rocks. The seepage also supports moss, algae, and other organisms, adding color and life to the cliff. All right, so these rocks are beautiful. You can now see clearly closer. This is the red mudstone, and we see conformable contact over here. We see conformable contact. Can now see. Do you see now? This is the golden glow. This was the sandstone is having the color golden glow. That's where the name Golden Gate came from. All right, because during sunset, we are having this golden glow, and we're having these things and these beautiful caves because of the differences and grain sizes of the Clarence rocks. All right, so this mountain or this cliff is right in front of the Hodimodumo Center. In conclusion, the rocks of the Golden Gate Highlands National Park record a journey through Earth history, braided rivers of the Molteno, floodplains of the Elliot, with the dinosaurs and mass extinctions, desert dunes of the Clarence and the fairy lavas of the Drakensberg, dikes, sills, quartzite caves, and black streaks add detail to this geological tapestry. Together, these features make a park a natural classroom of geology and paleontology, preserving evidence of ancient life, climate change, and tectonic upheavals, all while creating one of South Africa's most iconic and beautiful landscape. That's why the Golden Gate is regarded as one of the best geoheritage site in South Africa, attracting researchers, attracting students, lecturers, teachers, and tourists, of course. Okay. So thank you guys for joining us in today's lesson. I hope it was a quick one. I wanted to make it shorter and quicker, but I hope now you will be able to in greater detail as compared to the remember, like I said, we've started with the looking at the paleo environment and tectonic activity that shaped the Karoo sedimentation, and we looked into the entire stratigraphy from the Dwaika all the way to the Drakensberg. But now we zoomed in into the Stormbeck, and you were able to see structures and other things, and and be able to see the evidence of early Earth history. All right. Um, Thank you guys for joining us today. It was really nice being with you guys today. Please don't forget to like, share, and subscribe if you are new to this channel. And of course, you are enjoying our content. But above all, don't forget to hit the notification button below so that you get notified once we upload new content. And I'm sure you know what I'm going to say. Until next time, cheers.